Hi guys, this is Bob Kramer. I'm here to describe our technique for insert welding, also known as plug welding. Tom Ferry and I came up with this technique about 7 years ago, and we had great success with it and have been able to do some really interesting Damascus and some representational Damascus that was very difficult to do prior to this technique. And so I wanted to share it with you today. First, I think we should talk a little bit about some history. Tom and I have been making knives in Damascus for about 30 years, and I just want to give some props to, all of the people that have come before us, going way back, thousands of years, whoever those brilliant people were that figured out how to take iron sand and turn it into steel, and then figure out how to forge weld it, and then, all the brilliant minds in the Industrial Revolution who figured out how to mass produce steel. This stuff is very difficult, and there are some brilliant minds, and a tremendous amount of research went into all of those things, and we are standing on their shoulders. And so hopefully we've taken some of the information that was put together by the guys in the American Bladesmith Society and all the brilliant minds of people making custom knives out there, and we just hopefully added on a little bit to that information, and we just thought it would be good to pay it forward today. And hopefully there's some people out there who could take this technique and take it even further than we've been able to do. Here are the machines that are really crucial, at least the way that we do it, and perhaps as you begin to understand the technique, you'll figure out another way to do it. On the left-hand side is our Protomax water jet, being guarded by Avi, who is Jess's dog, and now she comes to the shop every day, and she's guarding the Protomax because it's a really valuable piece of gear for us. We couldn't do this insert technique without the water jet. Protomax is made by Omax, and we were fortunate to be beta testers for this machine when it first came out about 7 or 8 years ago, and Omax gave us a really great deal on this, and it is a really beautiful machine as long as you are careful with it, and it's fantastic. I mean, it was designed for prototyping, and it's great for that, but for a small knife shop, this machine is incredibly powerful and can provide stuff that would be very difficult to do otherwise. And without this water jet, we would not be doing this insert technique. So we were fortunate that they came to us and said, hey, do you want to test it? So now we have this tool in the shop, and we began to stretch our minds and think, how can we incorporate this tool? Just besides making fixturing, how can we incorporate this into the making of Damascus? The middle machine is a rolling mill. It's a 10 horsepower, 3-phase, very powerful machine. And I'll explain in a bit how this machine serves us for this particular technique. It is not essential that you have a rolling mill, although it can be very helpful. The other machine that is crucial to this operation, at least from my perspective, is the machine on the right, which is a coining press. That's a 160-ton coining press. And then if you look in the press, there is a fixture that we have made, and that fixture is crucial to at least the way that we do this technique. Here's one of the first insert welds that we tried out just as an experiment. We began with simple geometric forms. The piece on the left you can see is a random Damascus background, and we have inserted and welded 3 geometric shapes, a circle, square, and a triangle. We really felt like the triangle and the square were going to be difficult to do. It was not captured. In other words, the background Damascus was not captured. We essentially cut the holes and cut the plugs on the water jet. And when you create your tool path for your parts, you're going to want to offset to cut on the inside of the line for the female portion of the insert, and then cut on the outside of the line for the male part. So for the part for the insert, which I'm going to call the male part, that part needs to be slightly bigger. So you're going to get kerf with the water jet, and you have to account for the kerf. Your parts need to be a little bit bigger, the holes need to be a little bit smaller, and ideally you want to have to tap those parts into place. Your inserts are going to be cut from thicker material than your background material because you need some material to be able to squish out and actually fill up that void. And we want the inserts to be squished first before the background actually sees any pressure. In an attempt to etch this material a little bit deeper for a better photograph, you'll see where I accidentally left this in the etch overnight. I put it in, I forgot about it. But the cool thing is that you can see the weld, particularly on the square piece and the round piece. It is welded to the center of these things. Another way of putting it is that it doesn't just weld on the surface, but those parts expand and fuse all the way to the outside. You can tell that the weld is more susceptible to the acid. That said, once they're welded, they're in. Our first attempt was with these dies. We made these dies for my 60 kilo power hammer, and these were made out of 4140, and we made these dies sort of high so that we could very carefully forge the bigger inserts and kind of squish them out so that they would match the background material, or that they would compress first. Although this worked, it also distorted the material, which is not what we wanted to do. So we used these for a few tests and then came up with another way to kind of go about it. Here's a shot of the coining press with the fixture in place. So this fixture is a heavy duty. That bottom plate is an 1.25 1.5 thick. So the base plate and the sides and the back are all 4140 heat treated. They're drilled and tapped, and so those capture the bit of steel. Once it's up to temperature, it fits just inside this compartment and actually protrudes above this fixture or that cavity, so that when the coining press is activated, our work is standing proud of that surface and gets compressed by the coining press. Here's one of the first projects that we had. We made a couple of knives to auction off for the International Rhinos Day, and the top knife is a mosaic Damascus that we cut the negative space, or the female side of this insert weld, and then we cut the rhino out of a random Damascus and inserted that into this knife. On the bottom was just flipped. We had a random blade and a mosaic rhino in there. Now there were a couple of things where we noticed that the rhino almost disappeared to some extent in the pattern. It is surprising how well these things can blend. You know, you think you've got two different Damascus patterns and they'll just pop, they'll just stand out, but that's not always the case. And so with these two particular pieces, we made the decision to have Tom engrave the perimeter and then insert 24 karat gold to really make these rhinos pop. Here's a variety of knives that we've done over the years with various inserts. We'll start from the left-hand side. That insert of the arowana is a high nickel material that we cooked up in the shop, and fairly low carbon, so it's not really hardenable, and that allowed Tom to hand engrave all the scales on that fish and all the fins. Now all those silver scales that you see in the background material, those are all plugs. This particular knife had a lot of parts that all had to get fused together. Next knife to the right, we've called the Last Salmon, and it depicts orca whales. There's a lot of orcas where we live in the Pacific Northwest, and those orcas are multiple pieces. So the body is one piece of dark Damascus. The silver parts on the orca are high nickel inserts, and they're all forge welded to a background of high layer count Damascus. And then the salmon up in front, that is a high nickel steel, again, fairly low carbon content. The next piece over is probably one of the more complicated things we've ever done. We call that Queen Bee. All the flowers are inserts into a random Damascus background. Tom hand engraved and inlaid 24 karat gold bees into the blade. The next piece over is an homage to M.C. Escher. I've always been inspired by M.C. Escher's work and his tessellations. And just for grins, we said, oh, let's try it. Let's see if it'll work. The background is a random Damascus, and then each one of those Pegasus horses is a high nickel steel, similar to a 15N20. So again, lots of parts in this piece. I actually did not think this blade would weld up because of the amount of surface area that needed to be accounted for. In fact, this blade welded up perfectly, which we were surprised at, and was a real pleasure to finish out. Next piece over has some mosaic plugs in a random Damascus background. Next blade over is a bunch of koi that was actually one of the earlier pieces we did, and that combination seems to work really good. A random Damascus, kind of an organic feel to it with the koi inserted. The polar bears, each one of those ice flows is a separate Damascus. The polar bears are high nickel material without a lot of carbon, and Tom hand engraved all of the fur and physical features of the face on both of those polar bears. Really, really outstanding engraving. Next piece over again is a bunch of mosaic in a background of random Damascus. Next one over is actually a random Damascus dragon inserted into some water quenching steel. So we were trying to get that effect of sort of a dreamlike cloud dragon and the hamon as well. And then the last piece to the right we called Diamond Girl. Again, you can just see the variety of what is possible. Here's a picture of the inserts, and they are sitting atop of the background material. So we cut the inserts out of some material that is close to a 1/2 inch in thickness, and the background material is around 300 thousandths in thickness. Here is a picture on the left of us cutting the blank out, so it's to the right shape, so it actually fits the fixture that goes into the coining press, and that is a real specific dimension or relationship between the size of the background billet, and then you can also see the negative space or the female cut of the two koi fish, and then the two inserts, and keep in mind the two male inserts are actually thicker than the last piece at the lowest portion where you see the negative space of the koi. And you can see the amount that they actually protrude from the background material. I'm actually pushing nickel powder into any voids that may occur in between the insert and the background material. I'm actually applying a little bit of watered down white glue, or Elmer's glue, basically PVA, to surround the fish and keep that nickel powder captured between the male insert and the female background material. And then the picture to the right, I'm actually drying that PVA out so that I can then apply nickel to the other side to try to get as much material between the male and the female part as possible before I put the caps on. So here we are. This is a different pattern that we're assembling, but what I want to show you is the caps that we weld in place. So the top and bottom cap, we happen to use 15N20 at the shop, but I think you could use mild steel. I like 15N20 because of the nickel content. It tends to be a little bit stiffer and therefore has less of a propensity to squish out and move or be soft underneath the coining press. In other words, the top and bottom caps are stiffer, and so then when pressure is applied, that pressure is more directly transferred to the insert, and that's the piece that I want to squish or spread first. Once we put the top and bottom cap of the 15N20 on, then I'll MIG weld a seam all the way around to seal that enclosure. Oh yeah, so I've just MIG welded the perimeter of this, and I still have the ends to weld up. But that way, everything is clean on the inside. There's very little oxygen in there. And as this billet starts to come up to temperature, that PVA will burn off and it'll consume any oxygen that's within this containment. And that way we prevent any scale from potentially occurring between the male and female parts prior to them welding up. I'm grinding the weld back to a very specific size, and that size is relative to my fixture. So I need to be sure that when I heat this billet up and it gets to welding temperature and that I set it in the fixture, that it will actually bottom out in the fixture when the coining press starts to exert pressure on this billet. If it's too loose, then as the coining press starts to exert pressure, then the background material will just squish to the left and the right. And I actually want to capture those two sides so that the inserts expand to the point where then they start pushing on the background material, at which point everything begins to weld. So here's the billet going into the coining press. You can see it's still proud a little bit. And now the coining press is doing its work, and it is forcing that whole billet back down into the fixture and compressing and forge welding all of those parts together. Now I put the piece through the rolling mill. I take it back up to a welding heat. Now we've done something interesting here in that my coining press, it only has room for about a 10-inch billet under the press. And so what we've done is compressed our imagery by 30%. So we've come up with our image like the koi, and then once we have our shape, we'll compress that to 30%. And then we transfer that to our water jet. So both the male and the female portions of this insert weld are actually a compressed image. And so once I've gone underneath the coining press and forge welded all of that stuff together and then taken a reheat on the billet, once I put it through the rolling mill, it will actually expand or reinflate that image to full size without distortion. And this was something that we had talked about, a knife shower to hammer in. I think Ed Shemp was involved, Tom Ferry was involved. I was in on it. I can't remember who else was there, but we were curious if you actually compressed an image and then put it through the rolling mill, if it would expand back out. Ed Shemp had a gathering for the Planet Project. Boy, I want to say this was maybe almost 20 years ago. And Tom Ferry had some parts cut, and I believe it was a horse, and he forge welded that to a background. So the horse was compressed, and he forge welded that to a background material, and then we put it through Ed's rolling mill, and the horse expanded and looked perfectly natural and normal once it was reinflated. And the calculation is flawless. It works. In other words, if you reduce your image by 30%, and then you measure the thickness of your material and compress it by 30% under the rolling mill, it'll reinflate to the perfect image size. All right, so here's an image of surface grinding. On the left-hand side, I'm surface grinding the caps, which are the 15 and 20 caps, off of the billet. And, you know, when the caps have witnessed a couple of welding temperatures, and there's actually some decarb, so you have to be careful to flip this billet multiple times. You'll take a couple of passes on one side, and then you'll notice the billet will start to curve. It'll actually want to come up off of the electromagnetic chuck, or in this case, it's a mechanical chuck. And so you have to flip the billet over and remove the decarb from both sides, and then slowly make your way down through the 15 and 20 to get to the core material where the imagery is. If you look very closely as you're grinding it, you can start to see the insert, whatever that is, reveal itself. And every once in a while I'll do a test etch just to see if I'm through the 15 and 20, because the 15 and 20 actually bonds to the billet as well. So you actually have to grind through it. The photo to the right is the billet ground, and then we lay a transparent pattern of the knife over the billet. We'll use this as a registration for how we want the knife to look, where the fish will be placed, or where the inserts will be placed on the knife, and then make a few marks with a Sharpie in critical positions, like registration marks, and then I can actually put a thicker, like a wooden template over the top of it, and then trace it and cut the knife out. Here's a short video of the phase shift of that knife once we've actually cut it out and are in heat treatment. And what's fascinating to me is how the phase shift occurs at different times, and that is relative to the chemistry of the steel inserts as compared to the background material. So the phase shift will happen at a different place, and the phase shift has to do with a change in the crystalline structure, going from a face-centered cubic structure to a body-centered cubic structure. And those things occur at different times because of different chemistries and at slightly different temperatures as well. Here's the knife after heat treatment, and again you can see the inserts stand out. They're different material, and so they react differently to basically all of the processes. Here's after it's been heat treated in a rough grind. We're not to a finished grind at all, but I did a quick etch just to see what the background material looked like, and also, just to see how the progress I was making. And sometimes I'm just curious. Sometimes I just want to have a look-see because it gives me energy. It thrills me to see these things inside here. But you can see the clear demarcation of the nickel outline, and then and you can see the difference between the chemistry of the fish in the center as opposed to the border on it. Here is the finished Meiji piece, and the inserts on this particular piece were a custom alloy that I made in the shop. It's about 95% nickel, 95% iron and 3% nickel, and no carbon in this fish at all, so it was incredibly easy to hand engrave. So I went in and engraved all the fins and the eyes, and highlighted the markings or the black spots on the fish. We had lots and lots of failures along the way. From the first couple of pieces I showed you, we were always looking to see when what was going to go wrong. So everything has to line up on this. If you get sloppy, it'll show in the work and you won't get a complete weld. Here are a couple of examples of those failures. The second blade in from the left, we were calling that a wizard's key, and this was going to be just a black and silver insert. I can't remember which component. I think the inserts were 15 and 20 and the background was 1080. And this occurred when my hydraulic press was needing a little bit of maintenance. I don't think it was quite putting out the full power that I thought it was, and this was a lot of surface area to fuse together, and consequently the inserts did not weld completely. They did not squish out completely to the edge. And so when I got to the point of doing the final etch, you can see where the acid attacked the perimeter or the diffusion bond area to the extent where, it was pretty clear we couldn't sell this knife. It just wasn't bonded up to the level that we wanted. And then the next knife to the right, that's actually a dragon insert, or one of the first dragon inserts. And what we were experienced was the same thing. We were not getting full pressure back at the tail end of the billet. So consequently, you can see these rust spots that we've got pointed out, and that's where the acid got in and just continued to eat away at the weld, and it wasn't a complete weld. The knife all the way to the right, while it looks like it was successful, when we put this under the microscope, we could tell that some of the welds weren't complete. They're camouflaged pretty good because the pattern is so complicated, or that there was so much activity going on. The faults in the weld can kind of disappear, but when you look closely, you can see that they're not good. And when you consider that this blade probably has about 7 or 8 hours of cut time, maybe more, maybe as much as 16 hours of cut time between the positive and the negative parts, and then the heat treat, and then the grind. And I mean, we even got to the point where we put the logo on it. It looked fine, but as I got to the point where I was going to put the bolster and the handle on, then it appeared, then the flaw appeared in the steel. And this blade all the way to the left is actually a perfect weld. Everything was running right, everything welded up perfectly, but after I put the mark on there and was going for the final etch, it just The pattern doesn't appeal to me. It looks like a bunch of Speedo swimsuits or women's underwear, or I don't know. It's just not right. So even though technically the blade turned out fine, it's just not something I wanted to put out into the world. And the point is that these blades take a tremendous amount of time and effort to put together, and then you kind of cross your fingers and hope that they weld up completely and that you like the pattern. If you have ideas or if you have questions, you can put them down below there. I don't post a lot of tutorials on YouTube, so if I don't get back to you right away, don't feel bad. It's just me not paying attention to YouTube. Thanks for watching. I really appreciate it. I hope this is helpful for you or informative, and take the ball, run with it. Love to see what other people get to do with this.